I want to thank Contemporary Calgary for inviting me to talk tonight, and also Charles Stankievech for putting together this awesome reflection on the science that we do and sort of how it can be interesting to folks that are not scientists as well. And that's sort of one of the most exciting things to me about this particular field of study, thinking about the origins of life. Okay, so this question, how did life begin, is so fundamental that it has been pondered since at least the times of the philosophers Epicurus and Lucretius, but likely by many indigenous people in the many thousands of millennia or thousands of years before then, right? So people that lived here in Calgary were likely thinking about this very question, and it is borne out in their traditions as well. And it is such a fundamental question because it is, it has to do with everything that we do, right? It is the part of science that ultimately gave rise to us. So how did life begin? And I've got two small children, and I love this book. It's called When Planet Earth Was New. It's written by two Canadians. And when you get to the part when planet Earth was new, and we'll talk about how old planet Earth was or is and how long it took sort of for life to originate. But when you get to the part where life originated, it just says life originated, and it shows you the seas, oceans, right? So at some point in Earth's history, life originated, perhaps in the oceans, but certainly in water. We need to follow the water to find the origins of life. And importantly, Gladstone and Diemert, the authors of this book, don't peg one specific origin hypothesis in the book. They ask the children who are reading the book to imagine an origin of life. And I hope that you're going to be able to do that as well today. I will talk sort of about the best bets that we have today about the scientific hypotheses for the origins of life, but I won't come with any conclusions. Okay, so when we think about and study the origins of life on Earth, we know Earth is inhabited, right? We're here, and it has been inhabited for some time. And we also have been studying Mars to try and understand the same process, whether life ever originated there. What we think about is this confluence of variables. First, and most importantly, is the solvent, water. Follow the water to find the life, right? So that's in the bottom corner there. Conditions, the temperature has to be such that the water is not steam or vapor. It can't be frozen, as far as we know, to produce the original origins of life. Other factors like pH and so on. At the top there, energy. So some source of energy from rocks or the sun or so on must be contributing to the original life forms. And then finally, the ingredients. C, carbon, H, hydrogen, N, nitrogen, O, oxygen, P, phosphorus, S, sulfur, which is a mouthful, so we like to say schnapps. Okay, so how did life begin is a very interesting question, and so we can frame it with this understanding that it must somehow involve ingredients, conditions, solvent, and energy. They all must come together in a confluence to generate the first life forms. But if we really want to put the context together, we must first ask, when? When did life begin? Right? We know that we are here today, but we know that humans have not been around for very long. When did the first life forms take root on Earth? And first, and I know this is a public lecture, so first thing we need to know before we talk about how long life has existed on our planet is how old is our planet? Shout it out. Does anyone know how old the Earth is? And I know I saw some geologists, so you guys aren't allowed to guess.
14 billion.
14 billion is the universe as far as we know.
4.5 billion?
4.5 billion years old is how old the Earth is. And to put that in perspective, Phanerozoic time, so the time of organisms we can actually see, has only been 500 million years, right? So 4 billion years of Earth's history that led up to the origin of Phanerozoic, or the organisms we can see, had life that was probably microbial, okay? So 4.5 billion years is how old the Earth is. So in order to put that in perspective, or in order to put the origins of life in perspective and the history of life on our planet in perspective, we must first know that. So then we have this diagram here that puts also a bunch of other key events in those first several billion years of Earth's history into perspective. So again, somebody shouted out the 13 or 14 billion years history of the universe. But the first thing up there that's probably most important for us here in our solar system is the formation of the sun about 4.568 billion years ago. Formation of the Earth shortly followed, 4.544. But the early Earth, not particularly habitable. Here it's illustrated as a lava planet, so a magma ocean. The whole planet was essentially molten at that time. And then shortly thereafter, the moon-forming impact happened. Theia smashed into the planet, probably about the size of Mars, smashed into the nascent Earth, and ultimately gave us our moon. But following that, we had finally the first confirmed ideas or signs that we believe indicate life on our planet. So by about 3.7 billion years ago, we have a history of isotopes that appear to have been laid down by organisms living on our planet. And then we have the oldest stromatolites, so those are rocks that look like they were laid down again by organisms. And then 3.4 billion years ago, so a whole 1.1 billion years after the planet originated, we have the first real verifiable microfossils. And then after that, oxygenic photosynthesis eventually originated, and then finally the Great Oxidation Event. So that's when we finally had enough oxygen in the air to start oxidizing rocks on their surface, and it would start to look much more familiar to the Earth that we know today. So in the first 2 billion years of Earth's history, so that's a very long time, again, consider that the life you could see has only been around for 500 million years, all of this action has happened. And the first life forms probably originated 4 billion years ago or so. Before that, it was probably too inhospitable for life to originate. Okay, so when actually did life originate? That we probably can't actually know, right? And I'll talk about the rock record from that time. It's very hard to constrain. But a very important component of this is that organic molecules that make up all of the known life forms on the planet today, they degrade in the presence of UV radiation. Okay, so if we don't have ozone in the atmosphere, organic molecules degrade quite rapidly. And so because of that, very smart scientists, such as Dmitry Sasolov here, say things that it is certainly conceivable that the organic synthesis phase, so the first part of this that actually led to then the first biomolecules, could occur on the timescale of weeks. Even hundreds of years seems too slow. So that means we're looking for a moment in time, less than 100 years long, in the 4.5 billion years of our planet. It's not very easy to find. Okay, and so here's a diagram showing, again, the history of our planet in terms of geologic time. Again, 4.5 billion years of Earth's history. There's our lovely Earth up there. Things that we've already talked about. The Great Oxidation Event happened around 2.5 billion years ago. We seem to have had a hydrosphere effectively, so water, liquid water on the surface of our planet for at least 4 billion years, perhaps longer. We have clear signs that water was interacting with rocks over the history of our planet. But this plot at the bottom here is effectively showing all of the rocks that we have preserved today on the planet. Very few of them are 4 billion years old. Actually, practically none of them. Just some small mineral grains are that old. And most of them are less than 1 billion years old. Which means that if we want to try to find this moment, perhaps less than 100 years long, in the 4.5 billion years of our planet, we're either going to have to find a needle in a haystack or look elsewhere. Okay, so how did life begin? Again, this question that is so fundamental that we're thinking about tonight. It's important then, if we're going to try to find this needle in the haystack, we need to think about where did life begin, right? So we have some hypotheses for how did life begin in terms of the required ingredients, the required conditions, and so on. But where did life begin ultimately will help us constrain our search. And so this is a figure from a review paper thinking about the potential environments where life could have originated on our planet. One very popular one is shown on the right-hand side there. The deep hydrothermal processes or systems, so like black smokers or hydrothermal vents at the bottom of the ocean. Shallow hydrothermal systems closer to the continental shelves and places where you would have interaction perhaps with the atmosphere as well. Intertidal environments, rivers and so on, or hydrothermal fields, something like Yellowstone and so on. And then there's other perhaps less conceivable origins of life in atmospheric particles as well. So when we think about rocks, right, rocks that are 4 billion years old, the best chance we have of seeing them preserved are perhaps in hydrothermal systems or in hydrothermal lake settings on the ancient planet. Okay, and so if we think about Earth's history, and again we saw that plot of the fact that there's very few rocks that are 4 billion years old left on Earth, where can we go to look at what Earth might have looked like 4 billion years ago? Mars. Effectively, the youngest rocks on Mars are around 3.5 billion years old, right? So we see almost all the rocks that were ever created on Mars are still there today because Mars does not have plate tectonics. The crust is not resurfaced, it does not subduct, it's still there today. So those of us that think about these problems of origins of life use Mars as a well-preserved example of potentially the processes that happened on the ancient Earth that led to our existence today. Okay, so again, we follow the water, and interestingly and importantly, Mars has a very long but very early history of water. So these blue and red dots across this map are lakes, confirmed lakes on the ancient surface of Mars. And you see they're all over the place, particularly in the southern part of the southern highlands of the planet. And you see, again, that they're covering the planet, and there are particular places where we, humans who have been trying to explore again for the history of habitability on Mars, have sent rovers. Spirit, Perseverance, and Curiosity are all rovers that we sent to ancient lake deposits on Mars. So the first one here, Spirit, was sent to a lake, ancient lake deposit on Mars. Spirit died not too very long ago. Spirit was fueled by solar panels. Ultimately, its solar panels got covered in dust. It couldn't drive anymore. Curiosity, which is the one we're going to talk about most today because it's the one I work with. And then Perseverance, the youngest one on Mars, has been there for about a little over 2 years now, is also in an ancient lake and delta deposit on Mars. So again, we'll talk about Curiosity, mostly because Curiosity has the most published results and also because I am involved in the Curiosity mission and I know a lot about the data that's coming in. So here's Curiosity. Curiosity is actually quite a large rover, as you can see. It's larger than people. It's about as big as a car, as you can imagine and see. And Curiosity was sent with a whole payload, a science payload, to explore for habitability on Mars and the potential origins of life there. So there's lots of different instruments here, but in general, we have the ability to analyze chemistry, including organic chemistry, so potential ancient molecules that existed on Mars. We have a laser, the ChemCam instrument, that allows us to shoot even up to 10 meters away a laser at rocks in order to get their chemistry. And then it also has APXS, an alpha particle X-ray spectrometer, which is a Canadian instrument, was developed over in Ontario, which you can actually put on to the ground in front of the rover in order to get its chemistry. And then finally, we have instruments inside of the rover, the ChemIn instrument, which actually allows us to see the minerals truly in X-ray diffraction capabilities. It allows us to see the actual mineralogy of ancient deposits on Mars. Okay, so here's Curiosity. It's in a lake known as Gale Crater on Mars. And this is Gale Crater. So Gale is a very interesting crater on Mars because it's fairly young. It's about 3.5 billion years old, so not young in Earth terms, but fairly young in terms of the history of water on Mars. And also, it appears that Gale has about 4.5 kilometers of sediment in it. So effectively, the whole crater filled and seemingly overfilled with sediments. So we have a very, very long history of habitability at Gale Crater, which is why it was chosen. So it's been over 10 years, about almost 11 years at this point, that Curiosity has been on Mars. So there's its heat shield as it was landing on the planet, and there's its first image, and there's Mount Sharp in the background that it ultimately has been climbing for the last 11 years, looking at the history of habitability on Mars. And it's, again, touchdown confirmed, time to see where our Curiosity will take us at that time. And here's its pathway so far. So ultimately, it started here at Bradbury Landing in the bottom left-hand corner, drove across lots of ancient lake deposits, which we'll show in some images in a second, and has been climbing this Mount Sharp in the center part of the crater ever since. So right away, the first thing Curiosity did before it even drove anywhere was determine that ancient Mars was habitable. It had the ingredients, the energy, the conditions, and the solvent for life to have existed on ancient Mars. Whether that means it did exist or not is still unknown, but we have things like over on the right-hand side there, pebbles that were clearly transported by a river into the ancient lake crater and deposited on the bottom of the crater floor, and then also layered lake deposits over here as well. Clearly were deposited in a very deep lake, which is quite interesting because I didn't, it took me about a year working on the mission to truly understand how deep ancient Gale Crater Lake was. And so here's an artist's visualization of what ancient Gale Crater Lake looked like. So again, there's the central mound, so there's an impact crater. If you see the exhibit downstairs, a meteor hit into the surface of Mars, produced a central ejecta mound, and then ultimately lake water, groundwater filled in. I think of this essentially the same way I think of a quarry, a rock quarry here, if you have one in Alberta or anywhere in the world, where once you sort of stop mining it and you stop all of the pumps on the outsides of the mining quarry, it actually just fills back up with water. So this is what ancient Gale Crater Lake looked like. And because the crater is about 4.5 or 5 kilometers deep, the lake was 4.5 or 5 kilometers deep, which is quite an incredibly deep lake. Many parts of the ocean are not that deep. Okay, so again, ancient Mars was clearly habitable, and by analog, ancient Earth was very clearly habitable, but were the conditions right for life to begin? This ancient Gale Crater Lake, clearly a deep, potentially hospitable environment to modern life, but could the reactions required to originate life have happened there? Again, here, where did life begin is the last question we left with, and so now we can come back to the first question I asked is, how did life begin? So this is just one of numerous potential scenarios for the origin of life on our planet, but it seems to be sort of the best bet we have and has been the closest people have come so far to generating primordial organisms on our planet. And essentially what is required is wetting and drying. So filling the lake up with water and drying it down again. Filling it up again, drying it down in a cycle so that you can ultimately polymerize organic molecules, make them into the first protocells that then can go and populate the oceans. So looking at this and looking at that beautiful picture of the ancient Gale Crater Lake, perhaps ancient Gale Crater Lake was habitable, but perhaps it couldn't run this reaction backwards and forwards because it was just too deep. It was too wet. It never dried up. Okay? And so to think about that and think about evaporation cycles, we have another question, or I have another question here, to think about. So in order to put the rest of the talk into context, does anyone know how salty seawater is? How much by percent is salt in seawater? 1%, 10%, 90%? 6? you're close. I think I heard somebody say 3.5. It's about 3.5% salt, 96.5% water. So most of it's still water. And the evaporation cycles require that all of that water evaporates before you can then make a completely dry saline deposit. Okay, so here is Curiosity roving in Gale crater, shooting the laser at ancient rocks, and it has ultimately been using this laser to probe at geochemistry and potential mineralogy that might look like this cycle to go from wet to dry and back to wet again. So here's the ChemCam instrument again. It is co-sponsored by the French and the United States governments. And we have been studying, again, these saline deposits on the planet. And this is one of the few actual geochemistry plots that I'm going to show today. But you can see that the minerals that are all labeled there, things like anhydrite or gypsum and epsomite, those are all salts. Epsomite is Epsom salt, so magnesium sulfate up there is Epsom salt. And ultimately, we all know from experience that Epsom salt, if we dunk that into bath water, is extremely soluble. Basically, all that we can dump in is going to dissolve into the water. So in order to make Epsom salt by drying a lake deposit, we have to get to extreme extents of drying to do that. And so these analyses by the ChemCam instrument seem to suggest that evaporation cycles were happening on ancient Mars. And indeed, that was an exciting result for the mission, because we finally found this long-awaited salty region, perhaps this place where, first off, the planet is going through a global drying, but also, perhaps for the first time, you can run these wetting and drying cycles and originate life. And so this is a photograph, an aerial photograph from a drone of Basque Lake near Cache Creek in British Columbia. And this is probably something like what ancient Gale Crater Lake looked like when it was depositing these magnesium sulfate salts. Not particularly habitable looking, right? Especially after that beautiful sort of beach-looking image we looked at earlier. But it has, again, all of the ingredients. It has water, it has phosphorus, and all of the other schnapps ingredients. It has energy coming, again, from the sun in this case. And it has the right conditions. It has a habitable pH and so on. So this is probably what it looked like. All of the white stuff in between the individual ponds here is epsomite. It's magnesium sulfate salt precipitating. Actually, actively, it's one of the only places on Earth today that we can see this. It happens to be right in our backyard here in British Columbia. Okay, so now we're exploring the sulfate-bearing unit to understand how Mars habitability changed and ultimately how it could have been this time interval in Mars's ancient past that ultimately originated life. And so we see it here. It doesn't particularly look as defining as it is, but here's the clay-bearing unit, so something that is very familiar to us on Earth, things that form perhaps in deltas like the Mississippi River Delta today. Lots of clays washing into the crater. And then ultimately there's very few, if any, clays in those upper reaches of the mountain shown in this picture. And there's lots of magnesium sulfate minerals, things like epsomite up there. And so just to show sort of what this looks like in terms of chemistry, so evaporation going top to bottom here, where we start with a dilute water. We ultimately precipitate a bunch of minerals. You're probably familiar with some of these minerals: magnesium calcite, dolomite, and other potential minerals that are there. So gypsum, again, is the one that we mentioned, calcium sulfate. But ultimately, after you've gone through all of those evaporation and mineral precipitation, you make this mineral magnesium sulfate, or you make a magnesium sulfate brine. And Basque Lake in British Columbia is the type example of that. So that's why we've been studying those lakes in order to try and understand ancient Mars and the potential for originating life on ancient Mars. So this is sort of what it looks like. So as you evaporate, you need to evaporate a water on the order of 99.9% of the water needs to leave and you just leave behind that little residual scum, and that's how you get to the point where you're actually precipitating magnesium sulfate salts out of solution. Again, things like epsomite, which are incredibly soluble. And you make these sort of brine pools that we see at Basque Lake and ultimately see in Gale Crater as well, or the record of them in Gale Crater. So yeah, the ultimate conclusion here from looking at Mars' record of habitability and our understanding of Basque Lake is that magnesium sulfates, these minerals, epsomite being the key example, imply strongly evaporative conditions. Essentially, there is a global drying recorded on Mars by the fact that you're ending up with magnesium sulfate salts. You need to evaporate 99% of the water in order to get there. And that is apparently required in order to originate life. We need to have these wetting and drying cycles in order to do that. But life that could exist, that would originate in these environments, would struggle to survive because it ultimately, the water is drying and it ultimately could become too salty for life to actually live there. So again, how did life begin? And we are starting now to look elsewhere because again, if life struggles to survive in these magnesium sulfate rich lakes and there are incredible amounts of evaporation that must happen, we ultimately need to think also about other potential ingredients and places for life to originate. So here, again, the vital Schnapps elements are listed: carbon, hydrogen, nitrogen, oxygen, phosphorus, or sulfur. And which of these is the hardest to come by in natural waters? The hint is given by the tooth there. Does anyone know which of the Schnapps ingredients is the hardest to get in natural waters? Which is the hardest to find on Earth today? It's phosphorus, right? And I give the tooth because that's calcium phosphate or apatite or bioapatite in our teeth. And we're all lucky that phosphorus is not particularly soluble in natural waters because then our teeth would just dissolve into whatever we're drinking. So it's not very soluble, which is bad because we need it to originate life. And ultimately we need quite a lot of it, at least for all of the experiments that show the first biomolecules being formed. But most natural waters don't have quite a lot of phosphorus in them. But this one, which doesn't actually have any water in it in this photo, typically has lots of phosphorus in it. And I show this picture, actually I do lots of science outreach with grade school children. I showed this picture to a bunch of people, or a bunch of kids, I think in Oklahoma or somewhere like that, and they looked at it and they said, what's wrong with this picture? Why is there snow on the lake, but not on the grass around the lake? Ultimately, that's not snow. That's sodium carbonate, salt. Imagine all of the muffins you can make with all of that salt in that lake. This is an aerial photo of that, and you can see the little brine pools that still exist with enormous concentrations of phosphate in them. So again, phosphate in most natural waters is completely insoluble. It's at very, 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 very low levels. But here, in these little tiny brine pools that are located at the central parts of lots of these larger structures in the lake after it is evaporated, we see actually incredible amounts of phosphorus, the most phosphorus in any natural waters on the planet. So again, going back through this evaporation cycle from top to bottom, we can look at, again, we can go through these divides and choose your own adventure as you go down. And as you get closer and closer to the right-hand side there, these alkali valley or mono lakes, you get this sodium carbonate, again, that white salt that existed in that lake. It's mostly sodium and carbonate that make up that lake, so not like the ocean, which is mostly sodium and chloride, but there is a little bit of chloride there. And ultimately, quite a significant amount of phosphate as well. So here is just another chemical diagram showing the concentrations of inorganic carbon, so things like carbonate in solution, going up from left to right, and then the amount of phosphorus going up from bottom to top. And what you can see is that there are some lakes over there in the yellow dots, Goodenough and Last Chance Lake in British Columbia, that have more phosphate in them than any natural water on the planet. Specifically, Last Chance Lake, British Columbia, again, very close to Cache Creek, BC, about 10 hours west of here, has more phosphate than any water that's ever been analyzed on our planet. So British Columbia is the best place on Earth, right? To originate life, probably as well, right? Okay, so again, this wet-dry cycling figures prominently in all of the warm little pond scenarios for the origin of life. We need to totally evaporate the water, fill up the lake again, totally evaporate, fill it up again, in order to make these polymerized structures and gels that ultimately become the first nucleotides and cell walls and so on. And so in this process, perhaps what you ultimately make is biomolecules. And although we cannot confirm or actually really even technically interpret the origin of the organic matter we've seen on Mars, we have seen significant amounts of organic matter on the planet using the SAM instrument. So there's a diverse set of organic carbon-based molecules at multiple sites on ancient Mars that we've analyzed with the SAM instrument, but of course their origins are not yet known. So ultimately, we sort of have the evidence that these processes perhaps are making organic molecules. Maybe they never succeeded in making the first life forms, maybe they did, but we can see them happening on ancient Mars. Okay, so again, ultimately though, this transition to these salty magnesium sulfate producing waters, where there may or may not be enough phosphorus to make the first biomolecules, clearly indicate a transition to a less habitable environment. So clearly, based on the evidence we have, ancient Mars, greater than 3.5 billion years ago, was warm and wet. We have clear evidence of rivers, lakes, delta deposits, large crater lakes like that one we showed earlier. But now there's no water on Mars, right? And there's probably no living organisms on the planet. But that transition ultimately might have been the key interval in order to originate the first organisms there. Which is wonderful, right? So we finally have landed with a paradox, and perhaps we have some hope of making progress, right? We need that wet-dry cycling in order to originate life. Perhaps life took off here on Earth, and something they were doing was able to keep our planet habitable while Mars went the other way. Okay, so again, just to wrap up what I've been talking about, Earth has clearly been habitable and inhabited for a very long time, on the order of 4 billion years. So 4 with 9 zeros after it years. But we really don't have a good record of that on our planet because all of our rocks get subducted back into the mantle before becoming crust again. So ultimately, Mars may hold the secret to understanding how that came to be. How did our planet become habitable, stay habitable, and ultimately end up with intelligent beings such as ourselves? Okay, so I want to acknowledge that teamwork makes the dream work. I'm part of, again, the Mars Science Laboratory team. I work with my group at the University of Calgary, the Reactive Transport Group, to try and understand a lot of this stuff. And all of this has been funded by these various organizations, including NSERC, the Canadian Space Agency, and NASA.